So much of what we do as agricultural scientists, we do to account for and deal with and manage variation and variability, which is inherent in biological systems like the ones we use, or the ones we study, rather. Biological systems are very complex, and even seemingly identical individuals or organisms have differences. Environments also differ from year to year, from field to field, from season to season, from barn to barn, etc., etc. And most causes underlying variation are unknown and possibly unknowable. So let's give an example from a realm I'm familiar with: small plot studies of corn. So we can think of let's think of variation in yield, plot yield. So typically we measure yield. All the plants in a plot are harvested with a combine, and then we scale that up to yield on a per acre or per hectare basis. Okay, so it's not unusual for plot yields to vary considerably, even if we're imposing the same treatment or growing the same variety, applying the same amount of fertilizer. We get variation in plot yields. We have about 400 plants in every plot, and I just want to talk about a couple of the potentially random or unaccounted for processes that are generating this variation in yields from plot to plot. And this is variation we can't really account for as researchers or control. So here you see these are photos I took from the field, just showing how much variation there is from plant to plant in a small corn plot. Now, what's the cause of this variation? It could be multiple unaccounted for things. It could have been that maybe a plant was planted a bit too shallow or a bit too deep, or was planted on a rock, so it wasn't really buried in the soil, and that's going to change its yield. It'll increase it or decrease it. Maybe one plant was placed very close to a granule of fertilizer, so it got a lot more nutrients than its neighboring plants. Maybe there was some bird damage or some insect damage that affected one plant. These are all things that are random to us as the researcher. We can't really control. And so that these random processes scale up to the level of the plot, 400 plants, and it causes this variation from plot to plot. And we have to deal with this kind of random variation as researchers. So even though lots of the variation we deal with in agricultural science is unknown in terms of what's the source of this variation, we know it's in the background, and we always need to account for it in our experimental designs, be that spatial variation, temporal variation, or in animal science, it would be animal to animal or person to person variation. Let's give some examples of what happens when we don't account for this type of variation. Just because we don't know the source or underlying cause of background variation or unaccounted for variation doesn't mean we should not account for it. We need to account for it in the design of our experiments in agricultural science, even when we don't know the underlying cause of that background variation. And if we don't account for it, we're going to mislead ourselves. And here's two examples where I'm hoping to illustrate the point. So this is a Scottish farmer. She farms. This is wheat, and this is a tweet she put out. And I'm not picking on her. I mean, many people make this think this through, and this is very common to do split field experiments. So I do love a farm trial, nothing too complicated, but always good to try something different. So splitting MOP, muriate of potash, which is a fertilizer, on half of this field. And again, not knocking on this farmer. I don't want to pick on this person. But let's say they do this split experiment. They measure yield on the half that received MOP, yield on the half of the field that didn't, and they come out that, hey, it looks like MOP, this muriate of potash, reduces yield by about 10 bushels an acre. So what's going on, right? This farmer would probably conclude, hey, I'm not going to invest in this product. I'm not going to apply it to any of my fields. In fact, I'll probably never use it again. But when we look at, for example, unaccounted for spatial variation, this could be, for example, maybe one half of the field is very low yielding, and the other half of the field is much higher yielding. Maybe that's because of higher organic matter, or one part of the field received a lot more manure, over the years because it's closer to an animal barn or whatever. We have one half of the field that is just naturally higher yielding and another half that's naturally lower yielding. And if we don't account for that spatial variation, then our results are going to be misleading. And that's possibly what happened here. I'm just making this up. this map up. So we're going to talk a little bit about how you deal with that in another lecture, but you need to account for it. And you do that generally. We're going to talk about how you do that in a minute. Here's another example of not accounting for random variation in an experiment and how it can be misleading. So you have a herd of 25 dairy cows, and you want to test the effect of this ProLAC supplement on milk production. So this is how you decide to run the experiment. On March 1st, you take a random sample of 7 of your 25 dairy cows and you measure milk production. The very next day, March 2nd, you start supplementing your whole herd with ProLAC. All 25 of the cows are getting ProLAC. And then a month later, on April 2nd, you take another random sample. You randomly choose 7 cows from your 25 cow herd and you measure milk production. And then on that basis, the milk production on March 1st versus April 2nd, you look at did milk production change, average milk production, if it increased or decreased, you would attribute that to ProLAC. What is the farmer ignoring here? What are you ignoring here if you're the agricultural scientist doing the experiment? Well, you're ignoring the fact that, animals themselves will have differences in what their average milk production is. That can be based on age or just whatever, any other random reason. But if you're not measuring, for example, milk production on the same cow, you're just taking random samples, you might have results that are different, not because of ProLAC, but just because it turns out that the 7 cows you sampled the first time were just naturally higher in their average milk production than the 7 cows you randomly sampled the second time. And so we have to account, again, for variation in our experiments. So there's many causes of variation. Well-known causes of variation in agricultural research would be, in field trials, it would be spatial variation. So maybe one half of the field or a quarter of the field, or there's a trend, going diagonal across the field of increasing or decreasing soil fertility. So maybe soil organic matter is changing, maybe cation exchange capacity is changing, soil texture can be changing. In fact, soil texture does change across the field, and that's going to affect, for example, water holding capacity. And so if you're not accounting for that spatial variation, you're going to mislead yourself. We also have temporal variation. So from year to year, we might get warmer seasons or colder seasons or wetter seasons, drier seasons. And so if we're looking at the effect of muriate of potash in one year, it might be different than, the results might be different than in another year because it's just wetter or drier or whatever. And so typically we account for temporal variation by repeating experiments, not just once, but we do it, 2, 3, 4 years or more. In animal science, we also have to account for animal-to-animal variation. And so repeated measures studies are very common in animal science where we would look at not, a random sample of 7 animals, but we would take the exact same cow, for example, and we would measure milk production repeatedly over time, having given it ProLAC. And then we take another animal, measure milk production repeatedly over time on that same animal without ProLAC. Another kind of experiment we as agricultural scientists might do is a controlled environment study, be that in a greenhouse or a growth chamber. And we call it a controlled environment, but that is somewhat of a misnomer because even in a greenhouse or a growth chamber, we have plenty of variation and variability in the growing conditions. We have certain parts of the greenhouse which might be colder or hotter than others. We have areas that might be shadier or more sunny. And that happens because if you look at the roof, there's a lot of equipment dangling off of the roof, those whatever at the top of the greenhouse. And so you might have the sun being blocked in part of the greenhouse and not in others. And so we do have quite a bit of unaccounted for random variation in a greenhouse. And we actually, as a best practice, this is what you see as beans. We actually rotate those beans. We take those pots and move them around the greenhouse chamber to avoid, having a problem where, let's say, all of the treatments, a bunch of those beans are in a cold spot, it just so happens, or a hot spot just so happens. We randomize, say, every week we'll move these pots around. So we still have unaccounted for variation in quote-unquote controlled environments. We can also have measurement error. This is very true of instrumentation used in the field. This is an example of measurement error in soil moisture measurements, soil moisture sensing. Typically, we need 4 or 5 soil moisture sensors in a field to get a reliable or more accurate, precise measurement of soil moisture, because these guys are four or $500 a pop. They are not cheap, but they're notoriously unreliable. Without getting into the details, basically, even if you have the same soil moisture, the salt content of the soil is going to influence soil moisture measurements by the sensor. So the saltier the soil, not table salt, but like potassium chloride or calcium chloride, is going to influence your readings. And so it can be kind of inaccurate, and you typically need more than one sensor, and you average those values to get a more accurate picture of actual soil moisture. Another aspect of natural variation is the fact that treatment applications are also imperfect. And this just compounds the issue of background or unaccounted for variation we get in an experiment. So a very classic case for this is applying products with backpack sprayers. So be that a herbicide, a fungicide, a plant growth regulator. They're often applied in experiments, scientific experiments, with a backpack sprayer. And you have a person walking across the plot. That backpack sprayer is spraying at a constant rate. And so the total amount applied of that product applied to a plot depends on your walking speed. Okay. And so if you have people, you have the backpack sprayer set to whatever, 5 liters a minute, but you have some people that it takes 1 minute to walk across the plot, some people that it takes 1 minute and 10 seconds to walk across the plot. Well, you're having a little bit more product being applied to when those people are walking a bit slower. So typically, this is, again, an aspect you have to control for. Typically, people will use a metronome to get the walking speed correct. They'll use actually a metronome, like a tick, 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 and every tick is a step. And we also, as a best practice, have only one person applying the product. We're not going to have like 3 or 4 people doing this because everyone's going to walk at a slightly different speed, have a slightly different gait. And if you have multiple people walking at different speeds or the same person walking at different speeds, you're just compounding the background unknown variation because unknown to you, different amounts of this product are being applied. This is true for many, many different things, not just with a backpack sprayer. So far in this lecture, I've been talking about the challenges that variation poses to scientists, the fact that we have this unaccounted for random background variation. But we have weapons to fight back against variation, so to speak. Now let me be a little bit less violent. There are tools in the toolbox. And the number one tool in the toolbox we have as scientists to defeat variation, or at least live with it, is replication. Replicating. Now, what are we replicating? We replicate experimental units. What is an experimental unit? It's the smallest division of the experimental material such that any 2 experimental units can receive different treatments. This is awfully theoretical. Let me just go through an example by what I mean by replication, repeating experimental units. So, let's say we were doing an experiment and we wanted to test the effect of a given drug, let's say whatever, a pill you take. Now, would we test the drug on just one person, one patient, and then compare that patient to another one patient who received a placebo, a sugar pill? No, intuitively, we know that this is not how we would do a study of any kind of drug. We would want multiple experimental units, multiple patients. Again, the definition of that experimental unit is the smallest division of the experimental material such that we could impose different treatments. And that, for testing a drug on people, is individual people. We need multiple people, hundreds of or thousands of people in both group, those getting the drug and those getting a placebo, a sugar pill. And we get confidence that a drug has an actual effect if we consistently see a different response in one group compared to the other. For example, if we were just testing one person or 2 people or 3 people on the drug versus not on the drug, it might be that one of these people really likes to eat mango and mango just so happens to interfere with that drug. Or maybe that person is really, really, really unhealthy, or really, really, really healthy, like way healthier than average. But we don't know that when we selected them for the trial, right? So, people are unique, they're individuals, obviously. So when we have hundreds or thousands of people in an experiment, we know that there's this background variation. Some people are healthier, some people eat mango, some people don't. But we can account for that variation and deal with it by just having multiple replications of experimental units. And we have that confidence when we see consistently different responses in one group compared to the other. Now, consistency means differences between groups is larger compared to the variation within groups, which we can call random noise. Okay, between versus within group variation. Let me give a couple of examples illustrating the point. This is real data from a study that myself and Dr. Jinwook Kim are doing. He's a postdoc. And I won't get into the details, but basically we took a number of measurements on different varieties of corn. And here you see some data from 5 varieties, the kernel numbers per ear. So basically we grew these varieties and we took 50 corn ears, 50 ears of corn, and counted the number of kernels on each individual ear. Now, when we look at between versus within group variation, I'm showing you the distribution, the statistical distribution, kernel numbers per ear of 5 different varieties. And each variety is a different group because we have 5 groups here, you can say. So you have 5 different statistical distributions. Okay, so between versus within group variation. What we can first look at is the average value. So if we look at the variety B90J12, we can see that the number that is the highest frequency is the average of the distribution, and that's around 550 kernel number per ear. Now, when we look at the within group variation, so the variation in terms of kernel numbers per ear around the average, you can see it stretches from about 425 to about 625 or 650, but it's symmetric about the mean. And you can see that this is the size of the within group variation from about 425 to 650, let's say. Okay, now let's go to the next variety we're looking at, MZ2699. We also have the average here. Let's call that 500 kernels per ear on average. That's the average kernel number per ear for that variety. And when we look at the within group variation, so the variation in kernel number per ear just within that variety, the 50 ears of that variety, the 50 corn ears, it stretches from 350 to about 650. So when we think about the within group variation of MZ2699, it's a lot larger than the within group variation of B90J12. So we can compare how variable each individual group is. And I would say kernel number per ear in MZ2699 is much greater, much more variation within this variety in terms of kernel number per ear than the B90J12 variety, much smaller variation, kernel number per ear within that variety. So that was the within group variation in kernel numbers per ear within a given variety. When we look at between group variation, a very simple way to do that is just looking at the difference between the two means. And when we look at the difference between the two means of these two varieties, very, very small, right? Very, very similar mean kernel numbers per ear. So when we look at the between group, between the two varieties, variation is actually very small compared to within group variation. And so if we think about, is there a significant difference in terms of kernel number per ear between MZ2699 and B90J12? Probably not, because the between group variation is much smaller than the within group variation. And so there's probably not a statistical difference between average kernel number per ear between these two varieties. Another example of between versus within group variation, this is with made-up data. We have 3 different groups. So let's say we applied 3 different levels of fertilizer or whatever, 3 different supplements to a bunch of dairy cows. We have 3 groups, and at the top graph, within group variation is very, very large compared to between group variation. When you look at, for example, the distance between the mean of group 1 and the mean of group 2, it's very small compared to the variation within group 1 or within group 2, which means it's unlikely that there's a statistically significant difference in the mean value between those two groups. Now, you might look at the difference between mean 1 and mean 3, group 1 and group 3 average, and say, hey, maybe there's a significant difference there, but there's still quite a bit of overlap because there's so much within group variation. If you have, there's quite a bit of overlap between those curves. There's not a whole lot of differentiation in the top. If you look at the bottom graph, you look at within group variation is much smaller than between group variation. In fact, within group variation is much smaller. And the difference between mean of group 1 and mean of group 2 is very, very large compared to within group variation of either group 1 or group 2, and similar with group number 3. And so here we can see how between and within group variation is going to lead to differences in the statistical tests we're going to perform later in the course. Okay, just to revisit replication and experimental units, because experimental unit is really a concept I want you to have mastery over as we continue in this course. So, the experimental unit is the subject on which you are imposing treatments and taking measurements. I like the earlier definition as well, where it's the smallest division of the experimental material that you can make such that you can still apply treatments to two different units. So it's the smallest division of that material, but you can still apply a treatment to it. So when you replicate, you are replicating experimental units. You are not taking more measurements on the same experimental unit. And this can confuse some students because sometimes you think you're replicating, but you're just taking more measurements on the same experimental unit. So for example, let's say you wanted to measure average seed weight. So what's the average seed weight of in a soybean plant? And let's say you had 10 plants and you randomly sampled 3 seeds from each of those plants. You have 10 plants, 10 pots, 3 seeds per plant. You have 10 experimental units. Let's say you said, you know what, I want to be more precise. Instead of randomly taking 3 seeds per plant, I'm going to randomly take 6 seeds per plant, right? Well, now instead of you have 6 seeds per plant, but you still have 10 plants in 10 pots. So you haven't changed the number of experimental units. You haven't changed your replications. You've just taken more measurements on the same number of experimental units that you had earlier. One area of agricultural science this gets confusing in is when we think about yield, grain yield, which is something we often measure on a per plant basis versus a per plot or per area basis. Remember that the definition of agronomy, what agronomy is when you measure something on a per area basis, per hectare, per meter squared, per acre, whatever. That's the definition of agronomy. Whereas when we think about plant science, plant physiology, then we can start taking measurements on a per plant basis. So, grams per plant of grain. So if we're doing a greenhouse experiment and we're growing soybeans in individual pots, every pot has a single soybean plant, and we measure yield, then our experimental unit is the pot, is that plant itself, because each pot we can impose a different treatment in each pot, apply different levels of fertilizer or different levels of water, and we're taking measurements on the individual plant in that pot. So the experimental unit is the pot. If we have 36 pots in an experiment, we have 36 experimental units, okay? But when we're, say, doing a variety trial in the field, like what you see here, we have an individual variety of soybean grown 6-meter long plot. It's 1.5 meter rows wide. Our experimental unit is not the plant. It's the plot area. It's the individual plot itself. This is a variety trial in soybeans, so you can actually see the different hues, the different shades of green here. And we have our replications. We have 4 replications for every variety. And you can see that we replicate kind of in a rectangular fashion here. You can see our pathways. But you can see these are our replicates, and each variety is found in every replicate. We'll talk a little bit about that later in the course, how we would block a field treatment or a field experiment. But the key takeaway here is that the individual plant is not, we're not measuring yield on an individual plant. We're combining the whole plot, we're harvesting the whole plot and measuring yield on a per area basis, per plot basis, which is 6 meters times 1.5 meters is 9 square meters. So that's our experimental unit, the 9 square meter area of the plot, not the individual soybean plant. Another example of an experimental unit, and again, I want to hammer home the point. So let's say you're at McDonald's headquarters, you're in marketing, and you want to know if the chips and salsa is going to sell. And you want to know if people are going to buy it and if it's going to be a popular item. So what you do as a bit of a marketing experiment is you take 100 McDonald's restaurants that are all pretty similar. They're on a same city or similar neighborhoods or whatever. And you take these 100 and you randomly divide them into two groups. Half of the groups do not get the chips and salsa on the menu, and the other half do get chips and salsa on the menu. And you record how many customers walk into every McDonald's, for a 7-day period over a week. And you measure the proportion of customers, the percent that end up ordering the chips and salsa. So you're looking at what percentage of customers walking into the store order chips and salsas. What is your experimental unit here? What is it? It's the store itself. Because remember the definition of experimental unit, it's the smallest division of the experimental material that you can divide and apply a treatment to. And so the smallest experimental unit that we can divide up is the individual restaurant itself. Indeed, the measurement we're taking, the percentage of people who enter the restaurant and buy the chips and salsa, that's a proportion, a percent, and that is also a measurement being taken on the individual restaurant, at the individual restaurant level, because we're ending up with a percentage for every restaurant in the study. So the experimental unit here is the restaurant. So wrapping up here and leading into the next lecture, a second consequence of variation is that we can never state conclusions with 100% certainty. There's always a chance, a very small chance, that the apparent treatment differences were just due to random noise, random background with in-group variation caused by, we may not know what. So we always have to talk about confidence, scientific confidence, when we give conclusions from scientific studies. We have to give a level of statistical confidence in this case when we're talking about within and between group variation. We talk about statistical confidence, but there's also qualitative measures of confidence. And that's the focus of our next lecture. So takeaways from this lecture. First, I want you to be able to define and understand the importance of random variation in agricultural experiments, the 3 common causes of random variation in agricultural experiments, be able to give some examples of them, and to be able to look at a graph of normal distributions and look at how between versus within group variation can help us guess whether there are statistically significant differences between treatments. So understanding, looking at normal distribution curves, and then between versus within group variation. Finally, you need to be able to name and explain what an experimental unit and replication is. And obviously, these are 2 very tightly linked concepts in research methods.